welcome to Yellow Rabbit Mathematics. Today's topic is an introduction to integrals. So integrals are often described as the area under a curve. Probably the best way to start then is to try and visualize these graphically. So let's say we want to know some information about the area under a particular function. Let's take the function f of x equals x squared. So I'll put up here for us a rough sketch of the plot of this function. Again, labeling some of the important points here. We have the 0, point, 1, 1, 2, 4, and we'll go out to 3, 9. So here's the function f of x equals x squared. The area under this curve is any of this space here under the plot. To make things easier for ourselves, let's start with a small area. So let's say we're interested in the area under this curve from x equals 0 to x equals 3. So it's going to be this region right here. And we'll ask ourselves the question, what is this area? Determining this area exactly is at this point a little bit tricky because we have to deal with this curved function. What would be much easier would be to approximate this area as best we can using shapes that are easier to calculate. So the way we would do this is we can divide the area, divide this region into segments, all with the same width, construct rectangles based on these segments, and then add together the areas of the rectangles. So let's say, for instance, we divide this region, this area, into n segments. Each with width delta x. To start out, let's start easy. Let's make our n equal to 3 segments. That means the width of each segment will be equal to 1. So n equals 3, delta x equals 1. That makes my segments here 1, 2, and 3. The next step here is to form rectangles based on these segments, and we can do this in a variety of different ways. One way we can do is to use the value of the function at the left-hand point of each segment to form our rectangles. This is called the left-hand approximation. So let me abbreviate that. Left-hand approximation. So that would mean my first segment, left-hand point, is 0, 0, making my first rectangle nothing more than a straight line. Second segment, the left-hand point, is 1, 1. That makes my second segment rectangle this area. Third segment, left-hand point is at the point 2, 4, which makes that third rectangle the following. If I want to calculate the area, then I have to sum up the area of each of these individual rectangles. So I can write this. Area approximation equals the value of the function at the first point times the width, the delta x, plus value of the function at the second point times delta x, plus value of the function at the third point times delta x. So for this particular set of constructed rectangles, this would be areas 1, areas 2, areas 3, which is equal to first area 0 by 1, plus second area, height is 1, width is 1, third area, height is 4, width is 1, so I'm left with 0 plus 1 plus 4 equals 5. Clearly, however, if we take a look at our plot here, we can see that this is an underestimate, so it's giving us a value that's lower than the true area. That's okay, but let's try a different method and see if we can get a different result. So again, now let's start with our same 3 segments, but now instead of taking the leftmost point to approximate our rectangle height, let's take the rightmost point of each segment. So for segment 1, that would be this point here, 1, 1. For segment 2, it'll be this point, 2, 4. And for segment 3, this point here, 3, 9. So this gives us a new set of constructed rectangles. Since we formed these rectangles using the right-hand point of each segment, this is called the right-hand approximation. Let's abbreviate this. Right-hand approximation. We'll solve for the area the same way, summing up the area of each individual rectangle. In this case, the first one is a 1 by 1 rectangle. Second one, 4 by 1, and the last one, 9 by 1. So this gives us 1 plus 4 plus 9 for an area approximation of 14. However, this right-hand approximation, we can clearly see if we look at our graph, is definitely giving us an overestimate. So this is something larger than the true value. Again, that's fine. But let's see if there's another method we can take to get maybe a little bit closer. Our third method for approximating the area under this curve takes the midpoint of the function in each division to form the rectangles. So this will give us something that looks a little bit more like this. I'm taking approximately the middle of each section to form my 3 rectangles. Here we go. This is appropriately called the midpoint approximation. So again, we're going to add up the areas of the 3 rectangles we've constructed. Rectangle 1, since its height is at the halfway point, is going to be 1/2 squared, so 1/4 by 1. The second rectangle is constructed using this midpoint here, which is 3/2, so that gives us 9/4 by 1. And then the area of that final rectangle is 25/4 by 1. If I add up my 3 areas then, I get 35/4, or I can simplify this down to 8.75. Just visually looking at my plot here, I can assume that this is probably the most accurate estimate for the area under that curve that we've done so far. But it's difficult to tell if we're slightly overestimating, slightly underestimating. We're just not sure at this point. So wouldn't it be much better if we could find a way to more exactly or even exactly calculate the area under this curve? We can always improve our estimate by increasing the number of segments, which will therefore decrease the width of each segment. So for instance, we could divide this area into 6 segments, each with width 0.5. So we'd get these 6 segments here. This would help improve our estimate. However, we're going to need a lot more segments if we want to get anywhere close to exactly calculating the value. I could still write this out, however. I could write my area approximation. It's always equal to the function evaluated at one point times this width, delta x, plus the function evaluated at the next chosen point times delta x, all the way out to the final chosen point. If we've got a lot of terms here, it's easier to express this as a summation. So let's write this up. It would be the summation from the first point to the final point of the function evaluated at each point times the delta x. So this at the core would be the summation we would solve for a large number of points. One thing to keep in mind here is as the number of divisions approaches infinity, so as the value of n goes to infinity, the width of each division, this delta x, will approach 0, and the approximated area will approach the true area. Now, adding up an infinite number of rectangles, all with width approaching 0, would be extremely tedious. Fortunately for us, the limit, as n goes to infinity, is an integral. So it's the exact area under the curve. And we have a nice simple way of expressing integrals that I'll put up in the board now. The general form of an integral is as follows. We write our integral sign, which looks kind of like a capital S. We write our lower limit of integration, I'll just call it a here, it could be any value. And our upper limit of integration, I'll call it here b, of f of x, which is whatever function we want to integrate, dx. Dx here is the width of the divisions of the area we're integrating, and of course this value should be approaching 0. Just as an example for the problem we're trying to solve, our integral would look like this. Integral of the function x squared from 0 to 3. So here's what we're actually trying to solve to get the exact area under that curve. However, in order to solve it, we've got a little bit more to learn about integrals. So let's start thinking about integrals. First of all, how do we solve an integral? So one way to think about integrals are as antiderivatives, which is just what it sounds like. It's the opposite of a derivative. So the antiderivative of a function, let's say f of x, is whatever other function has the derivative equal to f of x. It sounds a little bit complicated, but let's write it down in the best form we can. If the function f of x is equal to the derivative of some other function with respect to x, let's just call that other function g of x, then that other function g of x is the antiderivative of f of x. So in the way I've written it here, g of x is the antiderivative of f of x. Let's do a practice problem to try solving for an antiderivative. So let's find what is the antiderivative of the function f of x equals x squared. What is this antiderivative? So first of all, we've defined our function, f of x equals x squared. In order to find the antiderivative, let's define another function. We'll call it g of x. We could call it whatever we like, whose derivative, so if I take the derivative of g of x with respect to x, is equal to my original function, f of x, which is x squared. In order for this to be true, and using what we know about derivatives, the function g of x must be some kind of polynomial, right? So g of x must have the form x to some power of n, and it can, of course, be multiplied by whatever constant makes it work. Substituting in this information, we can say that derivative of g of x is equal to, of course, derivative of this generic polynomial. And using what we know about solving derivatives, derivative of this polynomial would be a, the constant a, times n, whatever the value of the power was, times x to the n minus 1. In order for this to be a workable system, these two expressions for the derivative of g of x must be equivalent. So x squared must be equal to an times x to the n minus 1. We've now got two unknowns, constant a and the power n, that we'd like to be able to solve for. I can solve for n relatively easily. I know that n minus 1, in order for this expression to be true, must be equal to 2. Therefore, n is equal to 3. Next unknown, that constant a. Well, for these two to be equivalent, a times n must be equal to 1. Therefore, a must be equal to 1 divided by n, and since I've already solved for n, it's 3. A must be equal to 1/3. What does this tell me now? It tells me that I now have all of my unknowns, and I can go ahead and plug those in and solve for g of x. So let's write that over here. G of x is equal to a x to the n, so it's equal to 1/3 x cubed. If I take the derivative of this as a check, I'll get x squared, exactly as I would expect. So I've solved successfully for the antiderivative of the function x squared. But there's one more point to keep in mind. If I take the derivative of a constant, I get 0, right? So I have no way of knowing whether or not this is the full expression, or if it also contains some constant value being added to it. So to be safe, I always include a plus c when I'm solving for the antiderivative to take into account any constants. This c could be 0, or it could be 1, it could be -1, any constant value. Now we've successfully answered the question, what is the antiderivative of x squared? It is 1/3 x cubed plus c. So now that we've learned how to solve antiderivatives, let's turn our attention back to evaluating integrals. First of all, let's familiarize ourselves with the two types of integrals. So first type of integral we could encounter is called an indefinite integral. An indefinite integral is any integral that does not have defined limits. So for example, if I were to simply write integral of x squared dx without limits, this would be an indefinite integral. The solution to an indefinite integral is always simply the antiderivative. So since we've already evaluated the antiderivative of x squared, I can simply write the solution to this integral is 1/3 x cubed plus constant c, whatever the constant is, so exactly the antiderivative we found before. The second type of integral that we'll encounter is called a definite integral. So a definite integral is one that does have defined limits. So for example, if I were to now write integral of x squared dx with the defined limits of a lower limit of 0, upper limit of 1, this would now be a definite integral. Solving a definite integral is very similar to the indefinite integral. We'll start with the antiderivative, but we then evaluate that antiderivative at the two endpoints, and specifically we'll subtract the lower endpoint from the upper endpoint. So in this case, my solution would be the antiderivative evaluated at my upper and lower limits. So evaluated at the upper limit, this gives me 1/3 times 1 cubed plus c. I now subtract off the lower limit, so minus 1/3 times 0 cubed plus c gives me a result of 1/3 plus c minus c, which of course simplifies to simply 1/3. As you'll notice, when solving definite integrals, the value of constant c will always cancel out, so it would be perfectly acceptable simply to leave it out of our solution. Now we're finally ready to get back to our earlier question, which is, what is the integral, or the area under the curve, of f of x equals x squared from 0 to x equals 3? So what is this area exactly? And the answer is going to be an integral. So our area will be equal to the integral from x equals 0 to x equals 3 of x squared dx. Let's solve this integral. So of course, again, the antiderivative, we solved it before, 1/3 x cubed. Here I'm going to leave off the c because I know we're working with a definite integral. The c will cancel in the end because I'm evaluating this at my endpoints. Plugging in, I get my upper limit, 1/3 times 3 cubed, minus my lower limit, 1/3 times 0 cubed. Final result gives me 9 minus 0 equals an area of 9. So now we could successfully answer that question using our knowledge of integration. Be sure to check out the supplemental information for this video so you can see some common examples of integrals and how to solve them. This will help simplify your process of solving integrals and make integration relatively straightforward. Thank you for watching this Yellow Rabbit Mathematics video. I'll see you next time.